Hello. In today's video, we will be talking about the orbital speed of a satellite. Now, what is a satellite? As you all know, just like how all the planets revolves around the sun, in the same way there are certain bodies that revolves around these planets. For example, the moon. The moon revolves around the earth and it is called a natural satellite of the earth. But apart from the natural satellites, all the other satellites which revolves around other planets, there are man-made satellites that revolves around the earth. And of course on Mars, because we have sent certain man-made satellites on Mars as well, so that those satellites are orbiting Mars. But in this video, we're talking about satellites that orbits the Earth. Okay, so for example, the moon revolves around the Earth in a nearly circular orbit. Although the Earth itself revolves around the sun, but to study the motion of the moon around the Earth can be treated to remain stationary. And just like how we can assume that the Earth is stationary when the moon is orbiting the Earth, and for the study of the motion of the moon, we can also use that to study the orbital speed of satellites around the Earth. So when a satellite, okay, let me just draw a satellite. Let's just first draw the Earth. Okay, so this is the Earth and there's a satellite. Let's just say somewhere over here. So that's the satellite. That's a man-made satellite. So when a satellite revolves in a circular orbit, so this one is going around the Earth. All right. So this one is going around the Earth in a nearly circular orbit. A centripetal force acts upon that satellite. What is that force called? It's called the centripetal force. Okay, that acts upon that satellite. What is this centripetal force? A centripetal force is a force pointed towards the center of a circle, okay, that keeps an object moving in that circle. All right, so that's that's the definition of a centripetal force. So it's a force which is pointed towards the center of the circle. Now in this case, it's the force which is pointed towards the center of the Earth, okay, that keeps this satellite moving around. Okay, so that's the force. It is very much similar to the gravitational force, right? So in this case, we are going to call upon the gravitational force as well for us to understand the orbital speed of a satellite. All right. So the centripetal force on a satellite is given as the centripetal force is given as mass velocity squared divided by the distance. Okay, so what do you mean by this? What do you mean by this? So in our diagram over here, we can take the mass of the Earth to be me. So let me just write down mass of the Earth, me. That's a bigger m over there because it's a bigger object. And the satellite, the mass of the satellite, we can take it as m, little m right there. All right. And the distance between the satellite to the center of the Earth. So let me just draw a line over there, the distance from here to there. We can write it as little r. Okay, so that little r over there is the distance from the center of the Earth to the satellite. Okay, there will come there in this video. I'm going to talk about the bigger r, But don't get confused. This is the small r, and that is just the distance between this satellite and the center of the Earth. All right. So yeah, so this is the centripetal force is given. The formula is given as m. Okay, that little m. That means that's the satellite's mass because it's a little m over here, and the velocity at which that satellite is moving squared divided by the distance between the center of the Earth to the satellite, the distance between that. That's the little r over there. So this is your formula for the centripetal force. Okay, now let the mass of the Earth be me. We have already done that. Okay, the gravitational force which is exerted by the Earth on the satellite will be what? Well, we already know the gravitational force formula given by Newton. So we have force equals the gravitational constant, mass of the Earth, that's the mass of the first body, multiplied by the smaller body, which is the satellite, divided by that r squared. Okay, so as the gravitational force, this is the gravitational force formula. As the gravitational force provides the required centripetal force, okay, centripetal force, okay, then by clubbing these two, okay, one is the centripetal over here, one is the centripetal over here, and this one is the gravitational force over this side. So as the gravitational force provides the required centripetal force, we can combine these two. Okay, so let's just combine. Let's just combine these two together. And we can rearrange the formula and we can write it this way. The gravitational force would be equal to that gravitational constant, mass of the Earth, mass of the satellite, divided by r squared equals the centripetal force, which is mass of that the satellite, the velocity at which it's moving. So we can just write v, or if you want, we can say v naught. Okay, all right, divided by that r. It's the same thing. I've just combined both of them together. And now there are some cancellations. Okay, if you can see that little m gets cancelled. All right, and what else? Well, one r will get cancelled from over here. Then you're left with just one single r. And now let's just write this properly. All right, we will just get this v squared over here, v naught squared, and we can just write the same as it is, the gravitational constant, mass of the Earth divided by that r. And now let's just remove that square and put a square root over here. Okay, so I'm just removing the square. V naught equals, put a square root over here. That square, we take it out and put the square root over here and write the GME divided by that R. Okay, so this one, yeah, let me just box it. So this is your orbital speed of the satellite, All right, now in our example, in our example over here, the satellite was way over there, right? It was way outside. It wasn't right so close to the Earth. It had an extra distance, right? Now, what if the satellite is revolving very close to the Earth? Very close. Let's just say somewhere over here. Can you see that in red? Okay. Let's just say it's revolving over there. So if the satellite is revolving very close to the Earth's surface, then what would be the distance? In the previous one, we had mentioned that the distance would be little r, isn't it? Yeah, it would be little r. But in this case, we can write it as the radius itself, okay? The radius of the Earth. So that's a bigger r, the radius of the Earth, re. Because this little distance doesn't really matter. So if it's so close to the Earth, it just makes sense to give the distance between that satellite and the center of the Earth to be as the radius of the Earth itself. Okay, so now going back over here, now the question is, if the satellite if the satellite is revolving very close, okay, if it is revolving very close to the Earth's surface, then what would be the distance? The distance is going to be, well, r is actually now going to be re, the radius of the Earth with a capital R. Now what do? We can go back to this formula, the one which I have put it in the box over here, and then we can just write down, instead of the little r, we can just write the capital R. Okay, so here it is. V naught would be equal to square root of the gravitational constant mass of the Earth divided by that big R, the radius of the Earth. Now this looks a little familiar, doesn't it? GMER. Well, now we're going to talk about acceleration. Okay, now we know that acceleration due to gravity, well, what is that? What's the formula? Acceleration due to gravity would be equal to the gravitational constant mass of the Earth divided by that the radius of the Earth squared. Okay, so you must be familiar with this, the acceleration due to gravity. So we can just put the box over there. Okay, let me just give some space again. Now what? Now let me just go back. It's we can get this GME outside. Okay, let's just get that out. Okay, so that's GME, get that outside, and we club these two together. Okay, so that's G and RE squared, the radius of the Earth squared. And now you see that GME, which is equal to this GRE squared. Let me go up again. You see here, over here, instead of that writing that GME, we can plug in this figure now. Okay, so again, going back to this velocity, the speed, the orbital speed, going back and rewriting this one more time. So that's V naught equals, put the square root, G, that's acceleration due to gravity, the radius of the Earth squared, divided. So I hope you know what I have written here, what I've done here. What I've done basically is that, let me just color code this. I have written this, okay, over here. All right, so this is what I have done. So GRE squared, I have written this figure in the place of that GME, okay, because we know that GME is nothing but that GRE squared. So I'm just putting this figure right there, dividing with that RE over here. All right, so that's what I have done over here. I've just written that, and now I'm going to divide that. I'm going to divide that with that radius of the Earth. All right. So we can now do a little bit of cancellations one more time. So 1r gets cut off from here, and then you are left with v naught equals g, and that's just single re. So this is your orbital speed. This is your orbital speed of the satellite. Orbital speed of the satellite orbiting very close to the Earth. Very close to the Earth. When it is when it is orbiting very close to the Earth, we have just taken that r. Remember that radius of the Earth. That's what we have done. Instead of taking that little r, we have just taken the bigger one. And we played around with the formula, and then we came out with this. Okay, so this would be our orbital speed of the satellite orbiting very close to the Earth. This one over here is just the orbital speed of the satellite orbiting at some distance. Okay, orbiting at some distance. So let us just go back to this diagram. You can just see we started off with that little m, the mass of that satellite, which is orbiting at some distance. And we have taken that distance from the satellite to the center of the Earth to be as that little r. And then when we're talking about an object which is orbiting a body, and we have to invoke the centripetal force. So the centripetal force is just a force which is pointed towards the center of the circle, in this case the center of the Earth, and that's what keeps this satellite moving in that circle. And when we're talking about centripetal, we always talk about gravity as well. So gravitational force, um, which is given by this formula. And then we combine both of them, the force of gravity and the centripetal force, we combine both of them and write it in this way. We did a little bit of cancellations, and we got this v naught, that's the velocity of that satellite. We got that outward because we are talking after all about the velocity of the satellite. Okay, so why the velocity? Velocity is not just as you know, velocity is a vector quantity. Velocity includes magnitude and direction, and in this case you know that the satellite is going at a particular speed, and it is also changing direction each time because of that centripetal force. So it is going in a circle, and there's always this change in direction which is taking place. And every time we are talking about direction, we have to talk about velocity. If there is velocity, there is definitely acceleration. Okay, so in this case, so v naught squared, we got that out and we wrote everything as it is, and we got this squared taken off, and instead of that we have put a square root, and we came out with the orbital speed of the satellite at some distance. If the satellite is orbiting very close to the Earth's surface, then instead of taking that little r, we have given it the bigger r. We have taken the radius, the distance. We have taken the distance between that satellite and the center of the Earth to be the radius of the Earth. All right. And then we have just rewritten the formula that we got over there, that over here. That's what I'll show it to you. Okay, this formula. So we have just rewritten that. Instead of putting the little r, we have put the bigger r, the radius. Okay, and now since we're talking about velocity, and definitely we have to talk about acceleration. So now acceleration due to gravity, the formula for acceleration due to gravity is g equals the gravitational constant mass of the Earth divided by the distance squared. Okay, so this is what we have written, the radius of the Earth squared. Now we know that we can rewrite this statement by giving this GME, putting it outside, and clubbing these other two over here. So instead of writing this equation, we can rearrange this. Instead of writing GME, we have written that GRE squared, which we have done over here. So velocity velocity is equal to that g, little g. It's not that bigger g. Please don't make that mistake of writing the bigger g here. So this is the acceleration due to gravity g, and the radius of the earth squared divided by the radius of the earth. And over here, we just did a little bit of cancellations, and we're left with this formula, which I have boxed it, and that's the orbital speed of the satellite, which is orbiting very close to the earth. All right, and now we can just plug in the numbers. So we can plug in the numbers. We can say that g is the gravitation acceleration due to gravity is 9.8 meter per second squared. That's acceleration due to gravity. The radius of the earth is, I think, 6.37 times 10 to the power 8 meters. And now we can just plug in, we can just use this formula, this one over here, and just plug in. So that's V naught equals 9.8 times 6.37 times 10 to the power 8 all squared. And then you get something like 7.9 times 10 to the power 3 meter per second, okay, which is about 8 kilometer per second. Okay, so this is the speed of the satellite revolving very close to the Earth's surface, and that's about 8 kilometer per second. I hope you found this useful. Do let me know if you have any questions. If you want to discuss something, we can discuss that out. Please do write your comments in the comment section below. Thank you so much.